welcome. In this video, we'll be looking at areas under the x-axis and how to deal with situations where part of the graph is above the x-axis and part of the graph is under the x-axis. So let's look at this very simple function y equals to x. Alright, so f of x is simply x. Alright, so we could think of this as f of x here, and we want to find the area under the curve between, well, x being plus 1 and a minus 1. Alright, so we're going to integrate this expression x. So we are integrating x between minus 1 and plus 1. So let's see what happens. We're going to get this expression after the integration, and when we substitute 1 into the function and subtract the minus 1, subtract the lower limit, we actually end up with 0. What's wrong with this answer? Can you pause the video and have a go at it? And tell me, what do you think the answer is? Or jot it down for yourself. Alright, the area under the curve, these blue sections are not obviously 0. So why is it that this half, we have half here, minus yet another half is 0? So what went wrong? Is there an error in this squaring? Should we not have a squared minus 1? No, that's not the point. That's not the mistake. The squaring is fine. You just have to be careful. Alright, every time you have some limit, if you don't know the shape of the graph, you must consider the shape of the graph, because you're finding the area between the curve and the x-axis. So this area here is below the x-axis, and as I've said previously in the previous videos, I hinted that this area will come out as a negative. Alright, its absolute value is the answer. Alright, but it will come out in negative because we are really evaluating the function, and these value of the functions are really what we're doing with integration is really we adding up this f of x's together. These negative values are exactly the symmetrical value of these values here on the right. So in fact, in some cases you don't get 0, but your answer is not perfect, because part of the graph, let's say your graph f of x is here and you're integrating here. This area is positive, but this area is negative. So you actually, you're subtracting something from that area and you still get a positive answer, but you don't realize what went wrong because you didn't consider the shape of the graph and its roots and whatnot. So it's always important to graph the original function and see what's going on. So the correct way to go about this and finding the area actually is to take the absolute value when you substitute the limit, or basically uh, break it up into two parts. You know that from 0 on to 1 it's going to be positive. So here is the right side of the graph where you don't have to adjust anything. But here, if you notice, I put two massive big signs here. This means take the absolute value. So once we integrated this area, which comes out to be actually a minus here, minus, well, I broke this integral into two separate regions. Like I integrated between minus 1 and 0, and then I added the integral of 0 to 1. So integrating x between minus 1 and 0 gives us the same expression. So we using the same expression here, and only that the limits are going from minus 1 to 0, and then once I substituted that, this is 0, and this comes out to be a negative half. Now I'm taking this absolute value, which will be a positive half, and I'm adding this half to the other half there. so the actual area will be positive. Okay, so I hope that helps. The positive part, the right side of the graph, which gives you a half, we don't have to change it. Okay, so we said I've written in purple here for you that this negative half, we took its absolute value and we turned this area into positive half. Alright, so because, well, and if you think about it, if we cut this triangle and put it there, we have height and the width of the square is 1, therefore the area should be 1. Alright, so let's see another example. In this example, we got a curve of x and x minus 3. We multiply it out and you get two roots. Right from the factorized form of the graph, uh, you know that it has roots between 0 and 3. Now, this area is obviously under the curve, so the answer will come out to be a minus. Luckily, all of it is under the curve, so we don't have to break it into two separate intervals. We just evaluate the negative value and we take its positive answer. So the negative 4.5 will just take its absolute value and we write the answer as positive 4.5. The magnitude of the answer is important. There is no need to break it up into two separate intervals because all of it is already under the x-axis. Okay, this is the entire area under the x-axis. So magnitude is 4.5. So one more example here. This is going to give us graph of a cubic and its root would be at 1 and 0 and minus 3. So, and it's going to be a positive cubic. So when we picture it, we'll have a shape like so. At this is minus 3, 0 and 1. So these two areas are the areas we need to find, but this is saying that first we answered part A. We sketched the graph correctly. So then part B is saying to find the area under bounded by the curve and the x-axis. So what they want us to do is we know that this graph is going under the x-axis, so we evaluate that separately in a separate integral. We evaluate this 0 to 1 as a separate integral. We'll have a negative answer. I'm definitely sure about it. I can see it from the graph. Yes, you do this slowly and careful substitution. All these values, when you substitute 0 here, they don't have a constant, so they will cancel away, but it might be helpful to just write a note to yourself so you know you did this work. And finally, you get a negative 7 over 12. That's the area here. This is a small region under the x-axis. So we take its absolute value and we say 7 over 12. We put that aside. Now we integrating. Notice that this minus 3 must be at the bottom integral. So we start with the minus with the top and then subtract the minus 3 after the integration. The integration, you may cheat and you may use the same expression that you found previously. Notice previously. Now let's go back. What we did here was that we actually do have to go through the working out of expanding brackets and using those x and well, it's not actually too hard because there is just it turns into x squared plus 2x minus 3 and then you just multiply an extra x into it, becomes x cubed plus 2x squared minus 3x. So that needs to be done by you as well. No one's going to do it for you. And then if we can just cheat and just use the integrated version there and just substitute the limits into that expression, everything should be positive because all the area I can see already that all the area is above the x-axis, so all these numbers turn out to be positive. Yes, okay, we're subtracting some values here, but it gives us a positive answer in the end. So finally we add these two areas together because that's what we were asked to do. Alright. Notice now we're going to be devil's advocate. This final answer is 11.83, and we're just going to show you that what you could have done if you didn't use two separate integrals and did it all under one integral, what would be the problem there. So the correct answer is up here. We put that correct answer aside. That's 11.83. Notice this on the top corner, that's 11.83. Now, as just for an example, obviously this is the wrong method of doing it. Don't do it like so. I'm not saying this is going to be correct, just showing you why is it wrong. Because if you do that as one integral and don't take care of like the fact that it's going under the curve, the final answer will be 10.66, which is obviously less than the correct answer. So that's just saying that don't do it like so. This is notice the difference, okay? That's why we did that. Alright, so I hope you found this useful. I'll see you in the next video.